In this video, we'll be reviewing implicit differentiation. Again, that concept is the fact that we might have multiple pieces of a function that we can't actually take the derivative of as it is. So what we're going to have to do is apply the derivative as it is and then manipulate it to solve for dy dx. Okay? In this case, x times y, that is the product of two different functions, so when I take the derivative of a product, I must apply the product rule. So I'm going to go ahead over here, just like we normally do, is I'm going to identify f prime, g, and g prime. F I'm going to label as x, my g function I'm going to label as y, so my f prime is simply 1, because it's dx, and then my derivative of y in respect to x, because remember we're taking this whole function in terms of the derivative of x, is simply dy dx, again, or you can label that as y prime. I'd be cautious with using this notation again because that might look like y to the power of 1. And notice over here we do have y to the power of 2. So that might change things. I'm going to go ahead and consistently use dy dx when we're playing with implicit differentiation. So based on the product rule, this little section right here becomes the derivative of the first, which is 1, times the second left unchanged, plus the derivative of the second, which is dy dx, times the first left unchanged. Then we're going to go ahead and take the derivative of this stuff right here. The derivative of 3x is 3 times the derivative of x, which is simply 1. So I'm going to go ahead and put that in there. Plus the derivative of 4y squared. Now again, we got to be careful with this. This is the derivative of 4 times something to the power of 2. So it's going to be, carry down the 4, the derivative of y squared is 2y to the power of 1, times the derivative of the interior function. The derivative of the interior is the derivative of y. The derivative of y is dy dx. So now I've taken the derivative all in one step. Again, this is all one step. My next step is to use algebra to solve for dy dx. In that case, I will go ahead and manipulate some of these things ever so slightly, making sure that they're a little bit clearer to work with. Again, all I did was simplify. The next thing I'm going to do is I'm going to go ahead and subtract this 3 from both sides, and I'm also going to subtract that x dy dx from both sides. Again, my goal in the end is to get dy dx all by itself. For me to do that, I have to, again, move all my dy dx's to one side and everything that doesn't to the other. So this side is going to be y minus 3, while this side is 8y dy dx minus x dy dx. Okay, next I'm going to go ahead and factor out dy dx. End up with 8y minus x equals to y minus 3. And finally, in the end, I can get dy dx is equal to y minus 3 divided by 8y minus x. This covers using implicit differentiation, so we're going to go ahead and follow through with proving the derivative of the logarithmic function utilizing the exponential function. Okay, so I'm going to start with y equals e to the x. We know for a fact that the derivative of this function, y prime, is also e to the x. So if I look at the logarithmic function, y equals natural log of x. This is the function that I have, and I want to utilize this information up here to prove the derivative of this function. Well, what I'm going to do first is use a little bit of algebra, and by utilizing the algebra, I know that this function can transform into an exponential function. Again, one more time, from pre-calculus, all logarithmic functions are exponential functions in a different form. So now, if I rewrite this here just to be this, log base e of x, this is just a notational change. They are the same function, it's just a notational change. Then I can identify that my base is e, that every log function is equal to an exponent. Again, base e, every log function is equal to an exponent. And therefore, I'm going to have my base of e, my exponent of y, equals to x. Okay? So this provides us here now with an exponential formed function of this logarithmic. These two things are equivalent equations. Again, these two things are equivalent equations. So now I can use this rule up here to find the derivative of this thing. So I'm going to go ahead and utilize the appropriate notation to take the derivative of both sides of this function, d dx, on both sides of this function. Just like I did up here, I took the derivative of xy and got this. I took the derivative of this whole thing right here and I got this. So, in this step right here, I'm going to go ahead and do the easy part first. d dx of x is 1. That part's easy. Now, what is the derivative of e to the power of anything? Well, the derivative of e to the x is e to the x. So the derivative of e to the y should be e to the power of y. However, again, don't forget that chain rule must be applied if the derivative we're taking is in a different variable than of x. So this is in terms of y. My function that I'm taking the derivative of is in terms of x. So what is the derivative of a function of y in respect to x? Well, once again, dy dx. So now this provides us almost with the dy dx equals 2, but don't forget that natural, or e to the y is being multiplied by this. So to eliminate that e to the y, I'd have to divide both sides by that, providing me with dy dx equals to 1 over e to the y. Now, recall for a moment that the way that we did this work, this final result, is that dy dx was supposed to be 1 over simply x, correct? Well, also make note that we did change the form of this function to something else. So one way that we can manipulate this equation to validate and verify that this is supposed to be simply 1 over x is to take what y really is. Again, note, this is dy dx. This function, I'm going to put a question mark here, this function right here should be in terms of the variable x. Now in the previous implicit differentiation function, there was no efficiently way to solve this for y equals. But in this problem, if you look right here, y equals the natural log of x. So I can immediately make that substitution down here, which will provide me with 1 divided by e to the power of the natural log of x. But if we recall from pre-calculus, e to the power of the natural log of anything is equal to just that anything. Again, the note is, one of the rules of pre-calculus, e to the natural log of x is equal to x. If this base and the base of the exponential function match up, then I'm left with simply what was inside that exponential and logarithmic function combined. So sure enough, if I was given y equals the natural log of x, then my dy dx, in the end, as we stated before, is simply 1 over x.